The mathematical concept of a Hilbert space, named after David Hilbert, generalizes the notion of Euclidean space. It extends the methods of vector algebra and calculus from the two-dimensional Euclidean plane and three-dimensional space to spaces with any finite, or infinite number of dimensions. A Hilbert space is an abstract vector space possessing the structure of an inner product that allows length and angle to be measured. Furthermore, Hilbert spaces are complete. There are enough limits in the space to allow the techniques of calculus to be used. Hilbert spaces arise naturally and frequently in mathematics and physics, typically as infinite-dimensional function spaces. The earliest Hilbert spaces were studied from this point of view in the first decade of the 20th century by David Hilbert, Erhard Schmidt, and Frigyes Riesz. They are indispensable tools in the theories of partial differential equations, quantum mechanics, Fourier analysis, and ergodic theory, which forms the mathematical underpinning of thermodynamics. John von Neumann coined the term Hilbert space for the abstract concept that underlies many of these diverse applications. The success of Hilbert space methods ushered in a very fruitful era for functional analysis. Apart from the classical Euclidean spaces, examples of Hilbert spaces include spaces of square integrable functions, spaces of sequences, Sobolev spaces consisting of generalized functions, and Hardy spaces of holomorphic functions. Geometric intuition plays an important role in many aspects of Hilbert space theory. Exact analogues of the Pythagorean theorem and parallelogram law hold in a Hilbert space. At a deeper level, perpendicular projection onto a subspace plays a significant role in optimization problems and other aspects of the theory. An element of a Hilbert space can be uniquely specified by its coordinates with respect to a set of coordinate axes, in analogy with Cartesian coordinates in the plane, when that set of axes is countably infinite. This means that the Hilbert space can also usefully be thought of in terms of infinite sequences that are square-summable. Linear operators on a Hilbert space are likewise fairly concrete objects. In good cases, they are simply transformations that stretch the space by different factors in mutually perpendicular directions in a sense that is made precise by the study of their spectrum. Definition and illustration. Motivating example. Euclidean space. One of the most familiar examples of a Hilbert space is the Euclidean space consisting of three-dimensional vectors, denoted by 3, and equipped with the dot product. The dot product takes two vectors x and y, and produces a real number xy. If x and y are represented in Cartesian coordinates, then the dot product is defined by the dot product satisfies the properties. It is symmetric in x and y. xy equals yx. It is linear in its first argument. Y equals x1 y plus bx2 y for any scalars a, b, and vectors x1, x2, and y. It is positive definite for all vectors x, x0, with equality if and only if x equals 0. An operation on pairs of vectors that, like the dot product, satisfies these three properties is known as a inner product. A vector space equipped with such an inner product is known as a inner product space. Every finite-dimensional inner product space is also a Hilbert space. The basic feature of the dot product that connects it with Euclidean geometry is that it is related to both the length of a vector, denoted x, and to the angle theta between two vectors x and y by means of the formula. Multivariable calculus in Euclidean space relies on the ability to compute limits, and to have useful criteria for concluding that limits exist. A mathematical series consisting of vectors in 3 is absolutely convergent provided that the sum of the lengths converges as an ordinary series of real numbers. Just as with a series of scalars, a series of vectors that converges absolutely also converges to some limit vector L in the Euclidean space, in the sense that this property expresses the completeness of Euclidean space. That a series that converges absolutely also converges in the ordinary sense. Hilbert spaces are often taken over the complex numbers. The complex plane denoted by is equipped with the notion of magnitude. The complex modulus, z, which is defined as the square root of the product of z with its complex conjugate. If z equals x plus iy is a decomposition of z into its real and imaginary parts, then the modulus is the usual Euclidean two-dimensional length. The inner product of a pair of complex numbers z and w is the product of z with the complex conjugate of w. This is complex-valued. The real part of z, w gives the usual two-dimensional Euclidean dot product. A second example is the space 2 whose elements are pairs of complex numbers z equals. Then the inner product of z with another such vector w equals is given by the real part of z. W is then the four-dimensional Euclidean dot product. This inner product is Hermitian symmetric, which means that the result of interchanging z and w is the complex conjugate. Definition: a Hilbert space H is a real or complex inner product space that is also a complete metric space with respect to the distance function induced by the inner product. To say that H is a complex inner product space means that H is a complex vector space on which there is an inner product associating a complex number to each pair of elements x, y of H that satisfies the following properties. The inner product of a pair of elements is equal to the complex conjugate of the inner products of the swapped elements. The inner product is linear in its first argument, for all complex numbers a and b. The inner product of an element with itself is positive definite, where the case of equality holds precisely when x equals 0. It follows from properties 1 and 2 that a complex inner product is antilinear in its second argument, meaning that a real inner product space is defined in the same way, except that H is a real vector space and the inner product takes real values. Such an inner product will be bilinear, that is, linear in each argument. The norm is the real-valued function and the distance d between 2 points x, y and h is defined in terms of the norm by that this function is a distance function means that it is symmetric in x and y, that the distance between x and itself is 0, and otherwise the distance between x and y must be positive, and that the triangle inequality holds, meaning that the length of one leg of a triangle xyz cannot exceed the sum of the lengths of the other two legs. This last property is ultimately a consequence of the more fundamental Cauchy-Schwarz inequality, which asserts with equality if and only if x and y are linearly dependent, relative to a distance function defined in this way. Any inner product space is a metric space, and sometimes is known as a pre-Hilbert space. Any pre-Hilbert space that is additionally also a complete space is a Hilbert space. Completeness is expressed using a form of the Cauchy criterion for sequences in H. A pre-Hilbert space H is complete if every Cauchy sequence converges with respect to this norm to an element in the space. Completeness can be characterized by the following equivalent condition. If a series of vectors converges absolutely in the sense that then the series converges in H, in the sense that the partial sums converge to an element of H. As a complete normed space, Hilbert spaces are by definition also Banach spaces. As such, they are topological vector spaces, in which topological notions like the openness and closedness of subsets are well defined. Of special importance is the notion of a closed linear subspace of a Hilbert space that, with the inner product induced by restriction, is also complete and therefore a Hilbert space in its own right. Second example. Sequence space is the sequence space 2 consists of all infinite sequences z equals of complex numbers such that the series converges. The inner product on 2 is defined by with the latter series converging as a consequence of the Cauchy-Schwarz inequality. Completeness of the space holds provided that whenever a series of elements from 2 converges absolutely, then it converges to an element of 2. The proof is basic in mathematical analysis, and permits mathematical series of elements of the space to be manipulated with the same ease as series of complex numbers. History. Prior to the development of Hilbert spaces, other generalizations of Euclidean spaces were known to mathematicians and physicists. In particular, the idea of an abstract linear space had gained some traction towards the end of the 19th century. This is a space whose elements can be added together and multiplied by scalars without necessarily identifying these elements with geometric vectors, such as position and momentum vectors in physical systems. Other objects studied by mathematicians at the turn of the 20th century, in particular spaces of sequences and spaces of functions, can naturally be thought of as linear spaces. Functions, for instance, can be added together or multiplied by constant scalars, and these operations obey the algebraic laws satisfied by addition and scalar multiplication of spatial vectors. In the first decade of the 20th century, parallel developments led to the introduction of Hilbert spaces. The first of these was the observation, which arose during David Hilbert and Erhard Schmidt's study of integral equations, that two square integrable real-valued functions f and g on an interval a, b, have an inner product which has many of the familiar properties of the Euclidean dot product. In particular, the idea of an orthogonal family of functions has meaning. Schmidt exploited the similarity of this inner products with the usual dot product to prove an analog of the spectral decomposition for an operator of the form where k is a continuous function symmetric in x and y. The resulting eigenfunction expansion expresses the function k as a series of the form where the functions phi n are orthogonal in the sense that phi n, phi m equals 0 for all n_m. The individual terms in this series are sometimes referred to as elementary product solutions. However, there are eigenfunction expansions that fail to converge in a suitable sense to a square integrable function. The missing ingredient, which ensures convergence, is completeness. The second development was the Lebesgue integral, an alternative to the Riemann integral introduced by Henry Lebesgue in 1904. The Lebesgue integral made it possible to integrate a much broader class of functions. In 1907, Frigyes Ries and Ernst Sigismund Fischer independently proved that the space L2 of square Lebesgue integrable functions is a complete metric space. As a consequence of the interplay between geometry and completeness, the 19th century results to Joseph Fourier, Friedrich Bessel and Marc-Antoine Pascal on trigonometric series easily carried over to these more general spaces, resulting in a geometrical and analytical apparatus now usually known as the Ries-Fischer theorem. Further basic results were proved in the early 20th century. For example, the Ries representation theorem was independently established by Maurice Fréchet and Frigyes Ries in 1907. John von Neumann coined the term abstract Hilbert space in his work on unbounded Hermitian operators. Although other mathematicians such as Hermann Weyl and Norbert Wiener had already studied particular Hilbert spaces in great detail, often from a physically motivated point of view, von Neumann gave the first complete and axiomatic treatment of them. Von Neumann later used them in his seminal work on the foundations of quantum mechanics, and in his continued work with Eugene Wiener. The name Hilbert space was soon adopted by others, for example by Hermann Weyl in his book on quantum mechanics and the theory of groups. The significance of the concept of a Hilbert space was underlined with the realization that it offers one of the best mathematical formulations of quantum mechanics. In short, the states of a quantum mechanical system are vectors in a certain Hilbert space. The observables are Hermitian operators on that space. The symmetries of the system are unitary operators, and measurements are orthogonal projections. The relation between quantum mechanical symmetries and unitary operators provided an impetus for the development of the unitary representation theory of groups. initiated in the 1928 work of Hermann Weyl. On the other hand, in the early 1930s it became clear that classical mechanics can be described in terms of Hilbert space and that certain properties of classical dynamical systems can be analyzed using Hilbert space techniques in the framework of ergodic theory. The algebra of observables in quantum mechanics is naturally an algebra of operators defined on a Hilbert space. According to Werner Heisenberg's matrix mechanics formulation of quantum theory, von Neumann began investigating operator algebras in the 1930s, as rings of operators on a Hilbert space. The kind of algebra studied by von Neumann and his contemporaries are now known as von Neumann algebras. In the 1940s, Israel Delfand, Mark Naimark and Irving Siegel gave a definition of a kind of operator algebras called C**algebras that on the one hand made no reference to an underlying Hilbert space, and on the other extrapolated many of the useful features of the operator algebras that had previously been studied. The spectral theorem for self-adjoint operators in particular that underlies much of the existing Hilbert space theory was generalized to C**algebras. These techniques are now basic in abstract harmonic analysis and representation theory.